All right. Welcome back, everybody. Just a quick show of hands. Who's actually back? The people who answer within like 5 seconds are all my favorite people. All right. So that's roughly 2/3, and that's basically as high a response we ever get. So thank you for that. So I uploaded the notebooks to GitHub. You should now be able to open and see this. And then again, quick show of hands, how many people can actually see this? Perfect. All right, so yesterday there were a few exercises. So the first two were just questions that you could answer basically by copy pasting some of the previous material, but the idea was to get you to articulate it because it's easy to follow along and then say, yes, that's what cross-validation is, but to actually articulate and explain it is something which is pretty important to be able to do. In terms of the practical exercises, so this was just to show you the differences between regular and then large values for K and K-fold cross-validation. The last two questions were mostly the ones of interest. So the idea was to look at a very simple data set. So load digits loads a subset of a much larger data set called MNIST, which is basically just handwritten small digits. It's, in terms of, for machine learning, it's basically the Petri dish. So it's just like in cancer research. Cancer has been cured 100 different times in vitro. So the methods that work in Petri dish don't always generalize very well. So as a first sanity check, if you're trying to do some kind of classification, MNIST is a good place to start. So I just wanted to have people work with it a bit and then see if they could actually classify some of the numbers. So one of the questions here was, where are the mistakes coming from? So that was to get you to plot the confusion matrix that we saw yesterday. And then you'll probably have seen that some of the digits, or you might even be able to guess this, but some of the digits are kind of similar to each other. So the 4 and the 9, for example, are more likely to be confused for each other than a 1 and an 8. And then similarly for the 1 and 7. This last question was about reducing some of the number of pixels. So the images themselves are already pretty small. So they are 8 by 8 pixels, which is very small. But even with that, not all the voxels vary the same way, which means that not all the pixels, not voxels, force of habit. So not all the pixels are actually as informative as others. So for example, if you're going to write something and then center on that digit, it's very unlikely for the corners to be very informative of what the digit in the center of the image is. So depending on, so I haven't checked for the number of principal components that you could use, but you could probably reduce it by a fair number before you actually start running into significant changes in performance. There's a question about whether or not the solutions for all these would be posted, and yes, I'll upload them sometime over the weekend. Okay, so now move on to today's material. So this is going to be a bit of a contrast with what we just saw, which was mostly about model interpretation and causality and all these other things, but it does tie in very nicely into the larger theme. So in the first or second section, one of the things that we looked at was what overfitting was and why we would use cross-validation. So we had some amount of data that we took a ridiculous number of polynomial powers of, and then tried to fit our linear regression model in order to take advantage of the polynomial powers. Now, originally what we saw was that it worked well for the first power, it worked well for the second, and then gradually it just got worse and worse until it just got crazy and it looked like nonsense and shaking all over the parabola. Now, that's something that's relatively easy to detect using cross-validation. So you can train your model and then you can see, okay, well, yes, my model is overfit. Ideally, because not all models are a couple parameters, they don't all, you can't train 100 different models in less than a second because you're going to have too much data, your models are going to be too big. So one of the things to consider is computational time. So instead of having to train for days, train a model for days at a time, and then detecting that it was overfit and then fixing it and then iterating over something that takes several days again, we can instead try to prevent it from happening in the first place. So the question is, where does overfitting occur? And overfitting occurs when you've got too many parameters relative to the amount of data. So when we were increasing the number of polynomial powers, we just had more and more features, which caused our model to have more and more parameters. And the amount of data that we had was fixed. So we weren't improving explanatory power, we were just fitting to the training set. So how could we modulate our model parameters during training so that we can avoid overfitting? Or at the very least, so that we can reduce the effect of overfitting. And the answer to that is, as you probably guessed from the title of the section, is regularization. So regularization is a penalty which is applied directly to model parameters, independently of the model performance. So normally when we've used metrics in the previous exercises, we've only looked at model performance. And one of the things I said early on was a lot of machine learning doesn't really care about what the parameters are, we just care about how well it's performing. Well, regularization kind of says, okay, we don't really care what the parameter values are because we can't evaluate them directly, but we kind of have some preferences about what the general shape of the model parameters should be. So one example of regularization, which is listed here, is something called the L2 loss. And L2 is just means that we are taking the square of the values and then summing them. If we had L1, then we'd be taking the absolute value, and then cubed would be the power of 3 and so on. Normally, we only have L1 and L2. And these do have names which you probably have heard before. So L2 is also known as ridge. And L1 is known as lasso. So one of the questions that came up during the talk was how we can use these types of regularization. And that's what we're going to see in this section. So just to walk through the formula for a bit, we have, so if we just use an example for a loss, so this is the prediction loss. So this is the penalty applied to the model performance. This is what we've seen in the previous examples. The part which is new in the formulation is the second term here, which is alpha times the sum of the square of the weights. So sorry, not the weights, the model parameters. So alpha determines how much we want to balance between our regularization and our prediction. So if we're saying, no, we absolutely want to make sure that we minimize the model parameters squared, then we'd have a very large value of alpha. And then on the other hand, if we had very small values of alpha, what we're saying is, no, I want to make sure that my prediction is as low as possible. So here we're going to run through an example, which we saw. We're going to see an example using data that we saw in yesterday's exercises, which is just going to be our very noisy parabola. And we're going to, again, try to fit using our polynomial features. So just to know about using Sklearn, there are the different estimators will have, so some of the estimators are going to have a parameter which says specifically penalty. In the case of linear regression, this is implemented using a different method. So instead of linear regression, we use ridge. So you can see the import statement here. So if you're using another type of estimator, you may not see ridge SVM, but you can go find the different penalties in the arguments. So the first thing we do is we generate our data and then just take a look at it. And we can see that, yes, our zeros are at 0.2 and 0.6. If you squint a little. And it's roughly parabola shaped. So here what we want to do is that instead of training a linear regression, we'll want to train a ridge model. And first thing to always do is look at the documentation. So here we have the description, and then here are the parameters that we can do, or that we can specify. If you're not sure what they are, don't worry about them. One thing to note, define alpha. It's okay if you want to keep it at 1. We're going to modify its value later. Just make sure you define it so that you can refer to it more easily. And set fit intercept to false. The reason for that is in our features, when we're using polynomial features, the degree 0 is the intercept. So it's not necessary, it's not going to affect your result. But since we're going to be looking at the effect on parameter weights, it's a lot easier to visualize if we set it to false first. All right, so there's only a relatively small section to fill in. It's very similar to what we saw before. So I'll give you guys a few minutes, and once you're done filling that section in, raise your hand. That way I'll know when to move on. Okay, so a quick show of hands for who's finished this section. Okay, good. So it's really not that different than anything else in Sklearn. So it's just we initialize the model, and then we set the input parameters, and then we fit to our training data. So we'll see the effect of alpha in a second, but then if we run this cell, we run into some error. All right, the other. There's a misdefined variable somewhere in there. So here we have our ridge model, which we're just initializing, and then ridge model fit, where we just have our features. So that's all the polynomial powers, and then our training labels. Here, all we're doing is we are accumulating the list of, we're accumulating a whole bunch of things in the 3 different lists. So here we're getting the score for the training data. Here we're getting the score for the test data. And then lastly, we're evaluating the magnitude of the model's coefficients. So these are the parameters that are actually used to estimate the output. And then similarly, we're looking at the effect of the ridge model with all these same things. So in here, if we just execute this cell, it looks like a lot of things, but it's basically just formatting a plot. And then you should see something similar to this. So show of hands, who's able to generate plots similar to this? Good. All right, thank you very much. So we're just going to examine the what these plots are. So in the very top left, we just have the score versus the degree of the fit when we have just the linear model. So this is without regularization. So first we see that it improves very quickly, and then it just starts going down. If we look at the regularized one, we see that it goes up, and then it goes down not quite as fast. What's a bit more revealing is the shape of the predicted curve. So here, when we have just the linear unregularized model, we have all of these crazy shifts up and down, and that's because we have a very high degree polynomial. If we look at the regularized one, we have something which is a lot smoother. It still doesn't look right, but it's at least much smoother. Now, if we compare the total magnitude of the parameters versus complexity, normally if you add a brand new feature, what would happen is you'd have your previous features, which will still be similar, and then a new one. So you might expect it to go up, but this is only the regularized one. And the reason I didn't plot the linear one at the same time, because if you uncomment this line, so there's a comment at the end of it just telling you to uncomment it, this will display the magnitude of the coefficient in the linear case. This is why we don't code live. All right. So in black here is the magnitude of the coefficients if we just use the linear unregularized model. So you can't really tell anything's going on because at the very large degrees, the actual model weights are, the sum of squares of the model weights are just huge. So we'll just hide that real quick. So we just examined the difference between all we just examined the 4 plots, then we looked at the differences between regularized and non-regularized. So how does the performance differ across the two? So here, if we look at the actual test scores, we see that overall our peak here reaches 0.6, whereas the linear version goes up to something above 0.7, 0.75 maybe. And then for the prediction curve, the regularized one is a bit more satisfying. So what we're going to do now is that we're going to go back to the where we initialized the ridge model. And then we're going to change the values of alpha. And I'll give you a few minutes to look at the effect of alpha. So try to increase the value and then see what its effect is on the model parameter magnitude, the predicted curve, and the performance. And then see what the effect is of decreasing that same parameter. So I'll give you guys 2 minutes to play around with that. So the parameter that we're looking to modify, alpha, is all the way up here. So change that value up and down and then see what its effect is. So there was a question in Slack where the plot looks a little different. The plot that was actually posted there is kind of the plot I was hoping to get on my random fold. So that plot is perfectly fine. Okay, so if we, I think you guys would have had time to modify the parameters up and down a bit. So to understand, before we actually run it, let's get an intuitive sense of what we should expect to see. So here we're looking at the parameter alpha. If we go back to the formulation of it, alpha is the relative weight between the regularization loss and the prediction loss. So if we have very small values of alpha, so let's say that we set alpha is equal to 0. That means that we're basically going to ignore what the model weights are, the model parameters are, and then stick entirely to the prediction loss. So alpha is equal to 0 is equivalent to just simple linear regression. If we have very large values of alpha, what we're saying is we want to make sure that if you have a weight that it needs to very much, the higher the value of alpha, the more a feature needs to correct for the error to basically justify its own value. So if you have a very large alpha, you're going to have much smaller values for the parameters. So let's see what happens when we change this to, let's say alpha is equal to 2. Well, so when we double the weight of the regularization loss, we're restricting the model's ability to actually fit to the data. So it's able to fit something, but then we can see that the performance just is much worse. And the reason for that is the model is just over-constrained by by the regularization error. So it needs to have some leeway about how to change its own weights in order to fit to data. And if you decided to go very, very large, it would basically be fitting nothing. And then it wouldn't be able to actually make any kind of prediction because no feature could sufficiently explain the data. So what happens if we just decrease the value? So instead of 2, what if we just went the other way and then went to 0.1? So we run these 2 cells again. Then what we see is performance which levels off fairly quickly. So here we still see a peak early on, but then it just stops decreasing. So it doesn't seem like it's overfitting. It's still seeing the same data, so it has the same number of parameters, but it just stops without overfitting. And then if we look at the predicted curve, here we're still seeing the same mess as we did previously with, because this part hasn't changed. But then this curve is much better. So previously we'd seen that this was flat and then went up. Now we're actually seeing a curve to this. And the model parameters, we can see that this effect is kind of reflected here, where we have our highest number of, or highest amount of magnitude early on, but then after this, it just doesn't really change much. So this is a lot more, we can get some more extreme examples if we delve into the area of, no, this is a stupid number of parameters. So instead of 20, a power of 20, what if we did to the power of 50? And then regenerated this. Well, we see that, fantastic. So we see that for the linear model without regularization, it starts off just fine, and then it just gradually decreases. And then once you're way into the overfitting territory, it just goes crazy. Whereas the regularized one, sure, it goes down a bit, but it's fairly resistant to increases in complexity. And the predicted curve down here is even more exemplary of that. So here it's completely, as soon as it gets to the edge of the data, we see that it's pretty far down from where the other samples are. While it's in the center, it just goes up and down, still stays within some bounds, but this looks a little crazy. And then just as soon as we move outside of the range here, it goes crazy again. Our regularized curve, however, looks not really any different. And then same thing for the actual magnitude. So here we haven't changed the data, we haven't changed the model complexity, we haven't changed anything, and all we've done is constrain the shape of our model weights. So one of the very useful features of regularization is not just because it's popular, it's because it really prevents us from overfitting when we're not sure if we are going to overfit. So in the case where you've got a lot more parameters than you have, if you have a disproportionate number of parameters compared to the amount of data that you have, regularization is a very useful tool. Okay, so now I see like there's a bunch of questions, so I'm going to go through those real quick. This point, model parameter. All right, I missed the point how I should interpret the model param magnitude versus complexity plot and what it shows. So there, the point is more if you uncomment this line. So if you reran the plot, so the blue is the regularized one, the black is the non-regularized one. So the reason it's not super informative without the second plot is because the contrast is meant to show that the linear model just goes crazy. So here we can see the magnitudes here just correspond to these big drops. Whereas the regularized one is relatively smooth. So the actual model parameters don't change very much from one degree of polynomial to the next. Okay, so we saw that. So this question, does the order of the features determine which parameters are attenuated? No. So the features you can put in any order. it's going to give you the exact same result. So why does the regularized curve look similar no matter the alpha, and how should we interpret it? So the regularized curve so this one should look similar across the different values of alpha, and that's because the values that are most important are determined fairly early on. So if we had, so we can see this if we do something like, so if we had an extremely large value of alpha, we're going to see very different curves. So before it went down and then went back up. Here, this is just monotonically increasing. So it's less that it doesn't change with alpha, it's more that the model performance is going to be a lot more regular across increasing complexity. 0.1 is my favorite for this, so we're just going to leave that there. Okay. So there's a question about how do we choose the alpha, and we're going to see that in a minute. The answer is one of the two answers that are always the answer for machine learning, unfortunately. Good. So we saw the effect of L2 regularization in the proofs example. The other regularization that you may have heard of is L1, more commonly known as lasso. Instead of taking the sum of squares, we're looking at the sum of the absolute value. So intuitively, what would be the difference here? So in L2, what we're looking for, well, basically what it's saying is, it's okay if you have a bunch of weights, but if you have some which are very large, it's going to be more of a problem. What L1 is intuitively saying is, I don't care about the size of the model parameters, so long as they can justify their size directly to the prediction error. So it's a lot easier to work through the problem and then see the effect on the model parameters. So we're going to compare what happens to our data, what happens to our model, whether we're using Ridge or Lasso. So here we're going to go through a brief exercise, and then we're going to compare the two. And one of the things that we're interested in is just looking at the parameter magnitude. And I'd like for you to use a bar plot. That way we can directly compare the individual parameter values. So here we're not going to go through the entire loop. We're just going to do full-on degree 20 polynomial. We don't need the entire curve. So there's just a note if you're doing anything with these, there's a weird quirk with ridge.coef compared to lasso.coef. So you might have to do squeeze first. So that's just a numerical thing, not a machine learning thing. Okay, so the steps is we initialize and fit two models. We'll print the model parameter magnitudes, and then plot the parameter values for all 20 features for our models. And I'll give you a few minutes for that. There's nothing to fill in. My bad. Okay. Yeah, okay. So the reason there was nothing to fit in is mostly because depending on the values you choose for this, Lasso gives a bunch of errors about it not converging and things. So these will generally not give you an error or not give you a warning. And I didn't want people to freak out over all the different parameters. So these, the last two parameters are basically just constraints on the algorithm that's actually computing these things to make sure that it considers itself converging. So again, we can play around with these values of alpha. And then if we just run this cell, we can take a look at the magnitude. So not surprisingly, the one which penalized magnitude a lot more has a lower overall magnitude. But what's more important for this is to look at the different scores and look at the parameter weights. So in Ridge, which we saw previously, so that's the L2 loss, we see that there's few parameters which are large, but the actual overall magnitude is kind of distributed over a bunch of the parameters. Here, the actual values seem to be more focused on a few of them, and then for the very for the larger for the parameters on the larger degree polynomials, it's basically 0. So what that's basically saying is L1 looks for a sparse representation of your model parameters. So it's looking for as few features as it can. So if it can eliminate a feature that's not helpful, it's going to do so. Now, there's a question about whether you should do L1 or L2, and the answer is, so the question here is, when would you prefer one over the other? So if you have some information going into the problem that, yes, only some of your features are going to be important, then yeah, you might as well use L1. If you have some other information where it's just, well, it's going to be some mix of them, they're going to be, the actual values are going to be kind of similar, but I don't know what the values are for each one, then L2 would work. More realistically, what you're going to do is cross-validation and then check one versus the other. All right. So just a quick show of hands, who's okay with, okay, now the questions are coming in. But yeah, so we could have a quick show of hands for who's okay to continue. So this question about ElasticNet. So the question is, how is ElasticNet different from just tuning the alpha parameter? ElasticNet is a little silly because it performs really well, but at its core, what it is it modifies this equation. So instead of just having alpha times the weight squared, or having the alpha times the absolute value, what it does is it includes both those terms and then has a parameter which weights between them. So ElasticNet is a nice trade-off between L2 and L1. Then there's a question about, would it make sense to do feature selection and then apply lasso on top of it? We're going to see that later. And by later, I mean soon. And then lastly, how is the regularization determined? So if you're asking about the regularization weight alpha, that's cross-validation. If you're asking about whether it's L1 or L2, the answer is still cross-validation. So yeah, it's one of the nice things about presenting machine learning stuff is that the answer is basically always one of two things. It depends on the context or it's cross-validation. All right, so in the regularization examples, we saw the coefficient alpha, and that was used to weight between the prediction error and our regularization error. So the parameter itself is not directly part of our model. So it's when we fit our model, none of the data is actually used to modify the parameter directly. But as we saw based on the error for the L2 and did we do the score here? Yeah, and the score here, it does affect our model's ability to generalize. So although it's not a model parameter, it does affect how well our model does. So in the previous exercise, or yesterday's exercise, one of the things that we looked at was a logistic regression. And one of the things I pointed out was that we wanted to use a certain solver, so that's a background algorithm. And one of the reasons we had to do that was we had a small data set and some solvers work better with some types of data versus others. And it's not that you couldn't use the other ones, but the other ones may not converge and the result would be a non-optimal model. So any parameter which is not directly modified by our data is called a hyperparameter. So some of the common ones are regularization weights, learning rate, or even the sample weights. Sample weights, I think it'd be more like class weights, but so how we determine the best values for any of these hyperparameters is determined through cross-validation. So the example I really like to give as a hyperparameter is the type of solver, because it fits under that definition, but it seems a little crazy because it doesn't have a value. We're just cross-validating across algorithms. So here, if you could actually do cross-validation and then get the solver which produced the model which generalized, which you would expect to generalize better. Now, related to this morning's talk was the question of model interpretation. So if we examine the model parameters in the last example, and then compare them to the parameters that were actually used to generate the function, so or generate our data. So we used x minus 0.2 times x minus 0.6, which expands to this, hopefully. Math is hard. So both the model weights get in the general area of the correct parameter values. So these are the true values. So we want 1 times x squared, we want negative 0.8, and then plus 0.12. If we actually look at the parameter values here, they get it generally right. So we have a small value for the linear term. We've got a negative value for the linear term. Then we've got a medium largish value, depending on whether you used L1 or L2 for x squared. And then it also adds in all these other terms. So how would you interpret this model? So if we look at the parameter weights, is anybody comfortable saying that this parameter or this feature is twice as important as this other feature or this one? The answer is not really. So here, this is where I think it's kind of important to clarify something that Yarkoni said in the first talk. At least I'm hoping this is clarifying the way he intended. You can see what a model is doing. So the whole black box thing is, you can circumvent the black box thing and then say, yes, this is exactly what my model is doing. So here, if we look at a simple linear regression, we've got this weight, which is multiplied by that feature, and so on. So we can see what the model is actually doing, but interpreting it in a way that actually is meaningful is an entirely different question. So one of the things that was mentioned this morning is this is kind of where machine learning and scientists kind of separate a bit. Machine learning doesn't really care about what the model is. There is a box, we have our data, we want to predict the output. And as long as we can perform well and make those predictions semi-accurately, then we're satisfied. But typically, scientists aren't really interested in fitting to data. That's not always interesting. Scientists kind of want to have some sense of causality. They want an explanation for the data that we're seeing. And through that explanation, we can make predictions. So a lot of time, some people will ask the question, well, is this feature important for our output? You can't really answer that using the methods that we're looking at here. So we can't say this feature causes the output or this feature influences the output. What we can say about these models is this feature is useful for predicting the output, which is a very different statement, even if it sounds pedantic. It's the exact same distinction as what is correlation versus causation. So if we take a step back for a second, if you were to look at the number of hours studied by a student and then see how well they did on the exam, well, a priori, you don't really know whether studying causes good grades. So you can collect all that data and then make some plot and say, yes, I can predict whether or not they'll do well based on the number of hours that they've studied. But for all that you know, the amount of time that they spent studying is caused by their interest in the course, and their interest is what determines their grade. So the only way to actually make that causal is to first identify the feature of interest and then create an experiment and go back and accumulate and control your variables and have some kind of causal mechanism, which means you'd have to collect your data first, look at the features of interest, identify the ones that you're actually interested in, and then go get subjects and then tell them, okay, you study for 0.5 hours. You go to the next student, you study for X amount of hours, and thereafter that you'd be able to make some kind of causal statement about hours of studying does help with performance. So that difference is very important to keep in mind when we're actually looking at this type of model, or at the machine learning models compared to what you might actually be interested in. Okay, so one of the questions that comes up a lot is feature selection. And even today when we're looking at L1, there were a whole bunch of questions on how to do feature selection and how it made sense, and if L1 was kind of the same as feature selection and so on. So again, in my endless promotion of Sklearn, Sklearn does have a number of feature selection tools. So there's a link that's provided here, and there's a whole bunch of different ways you can use this. I just picked one for demonstration, which was RFE, which is recursive feature elimination. So what it does, it first fits your model to all your features and then gradually reduces the features. Then at the very end, it returns a list of features of interest, so the ones that helped predict the best. So in this next exercise, let me check. Yes, okay. Just want to make sure that wasn't filled in this time. So in this last exercise, we're going to generate a bunch of data as we did before. That code's already done. We're going to augment our data. Then we're going to initialize and then fit. So we're going to initialize 3 models: linear regression, which is our normal regression without any regularization, as well as lasso and ridge. Then we're going to use RFE to identify which features are ranked as most important for each model. And at the very end, print out the rankings for each of the 3 different models. In order to get to the actual rankings, after you fit RFE, you can get the rankings using your object.ranking. So I'll give you a few minutes for that. And then raise your hand on Zoom if you're done. Okay. So the format of the actual calls are a little different than just the fit. So here we initialize the. Oh no, did I not import it here? Yeah, okay, I did. So it's a little different than just fitting the model as we did before. It's closer to the cross-validation object that we had yesterday. So RFE just takes in the estimator here and the number of features to select. So here you can leave it as default, or you can change the value to something else. This will just say, how many features do you want as most important? So if you say, okay, well, I've got 20 features, but give me only the 5 that are ranked most important, then I'll just say, okay, well, these 5 are rank 1, and then give you a rank for all the other ones. So here we just do the same thing for each one, and then print out the rankings for the different features. If we run this cell, yeah, right. So if you see this, don't worry too much about it. It's due to like the tolerance being too low, and it not really converging as well as it thinks it should. So here we have the. No, let's actually label these. So here, according to RFE, so if we first did lasso and then did RFE, we see that the most important features are the first 4 features. Then if we go back up, so the first 4 features for lasso are degree 0, 1, 2, 3. So it includes just these, which kind of makes sense. It resembles our desired, or the generating function quite well. So we have values for the straight line and the quadratic. If we look at ridge regression, it says that, okay, well, the constant is not quite as important. The straight line isn't quite as important. Well, then the 4 after that are most predictive of your output. So if we go back up, so it says that this one is not so important, this one is not so important, but these 4 are. And it's kind of what I was saying earlier about the importance of the different model weights. You can't really rely on them to tell you what is important for prediction. Then lastly, for linear regression, you just get something which is nonsense. And that's not too surprising. We saw previously, like the model weights for the higher degree polynomials were just huge. And we know that at degree 20 for here, I think, yeah, degree 20, that linear regression just doesn't do well. So just based on its performance, we were kind of expecting this to be nonsense. Okay. So Jerome has been answering questions on the Q&A super well. There was a couple that I wanted to get back to, which I can no longer see. So there's a question of, is there a way around models that have missing data for one or more features? So that is, so the question missing data is a super common one, especially in medical applications or in medical contexts. There are a whole bunch of methods where you try to predict using a variable number of inputs. There are other ones where you first try to estimate what that value should be and then feed that to your normal model. So there are ways around it, but we're not going to cover that because it's a lot more complicated than is appropriate for this workshop. Is it possible to identify relevant features with more complex models? So we can do basically the same thing as we did for these simple models, but still for more complex models. So even for deep learning, for example, there is regularization there. If you want to do outright feature eliminations like we did with RFE, you can do that also. So we are fitting relatively simple data with relatively simple models, but all of these extend to more complex models and methods. There's also a question about, I forget the phrasing, what the difference was between PCA and feature selection. So yesterday when we saw PCA, we saw that we were reducing the number of features from 64 to 32. So there, we're not really eliminating features. What we're doing is reorienting them. So it's no longer a question of, okay, well, we're going to ignore the last 32. It's more, if you take 32 as the number of features you want to keep, it's going to take some combination of all 64 features that you have and then put those into your principal components, which are the parts of the data which explain the most variance. So PCA reduces the number of features that you have by combining a whole bunch of them to represent, to maximize the variance explained. What we're doing here with, oh, okay, Zoom just stopped or something? No. So here what we're doing with the feature elimination is that we're not trying to recombine them. We want to make sure that as soon as we eliminated a feature, we're saying, okay, there is no recombination. If I drop the feature, it is no longer considered in the rest of the data set. So they do both reduce dimensionality, but they do so doing very different ways. This question of, could you repeat the last exercise with more complex data by at least adding one more X variable and applying the polyphy over only X1? So if you're looking to just make the data more complicated, you can just do X minus. This is live coding with stuff I haven't looked at, so I know it's going to go wrong, but it's fine. And if we run this, yeah, of course. Oh, no, it's because that, I forgot that. Yeah, so this is due to the lasso fit. So if you want, you can actually play around with more complex data, and you should get, so you should be able to make similar conclusions. You just do this. Aha. All right, so what this does is that we have not only the x and x squared, we also have x cubed in this. And then we see the distribution is a little different, but we still see that for L1, we have a lot more zeros than for L2. So for L2, we've got this huge range in the middle of from 5 to 15 or so, which are comparable to the early polynomials. But for L1, they're basically all zero. Okay. So that is it for the content of the workshop. I'll upload the afternoon exercises shortly after lunch. One of the things I mentioned on the Slack and that is on the schedule is the data clinic. So if you'd like to get some help getting started with your own data and you'd like some pointers of where to get started, feel free to drop in and then we can take a look at it. You can put a message either on Slack or Patrick, Peter, you're around?
Yep.
Yes.
So do we have anything set up for Zoom this afternoon?
No, there's nothing scheduled. I think it was just the same program as the previous days.
Okay.
But we could set something up if participants wish to discuss live with us.
So what we're going to do is if you're actually interested and you like some pointers, send us a message on Slack, and then because it's kind of difficult to see what the issue is over text, we just might go over to a Zoom room and then we can take a look at your data a bit more directly. Lastly, so Jupyter Notebook that we've been using here is a very useful tool for demonstration and communication. In terms of development, it's not ideal. So one of the things that I've seen for people who are just getting to machine learning is to start doing all their assignments and all their code development in Jupyter Notebooks. And that's fine if you've already developed your code and you want to demonstrate what it's doing. But it gets very messy and harder to use if everything's in notebooks. So instead, what I'd recommend is something like an interactive development environment, an IDE. So one of the examples is PyCharm. So here it has some nice features, like you can see the directories, it'll coordinate with Git, you can commit things automatically, but mostly it'll do things like automatic completion and has a lot of nice features which actually help development instead of actively hurting it. So yeah, that was just a software development note. If anybody has any questions about either some of the material or anything, let us know on Slack.
Lex, is it fair to say that among the other advantages of coding in an IDE, like you just said, is far more flexibility for execution of your code later on, including multi-threaded advantages and things like that?
No. So one of the limitations for Python is kind of multi-threading, and like there are ways around it, but that's inherent to Python, not the environment. So the advantage for development environments is less performance or anything. It's really just code reuse. So it may not save your code anytime, but it will save people a lot of time.
Yeah, I think when I was thinking multi-threading, I wasn't thinking Python specifically, but some of the possibilities with some of the packages that are being invoked, including some of the things inside of Nylearn and things like that.
Yes, that's the thing I wanted to mention. So there's an additional package that we didn't get around to, which is called Nylearn, and it's a machine learning package which builds off of Sklearn, which is oriented more towards neuroimaging. So I'll put a message on Slack with a link to a very helpful tutorial on that. So Jerome is actually one of the developers for Nylearn. I don't know if you want to say a word or two about Nylearn, but
yeah, as Lex said, Nylearn, it's kind of a wrapper around scikit-learn that adapts scikit-learn estimators for neuroimaging data, and also has a bunch of stuff for plotting brain images.
So if one of the things that you guys want to be doing is actually visualizing some of your data, Nylearn does a really good job of handling specifically neuroimaging data. So Sklearn can still do it, but there's a whole bunch of helper functions that are neuroimaging specific in Nylearn that are super helpful.